Ever since the dawn of human beings, the one consistent thing that has driven us forward as a species has been curiosity. Our curiosity to explore the unknown has driven us to traverse every corner of the globe and chart the stars. As humanity sets our eyes on the world beyond the blue marble we call Earth and the comforting reach of our sun's light, we encounter quite an enormous problem. The universe is huge, and I mean really huge. The nearest star to our solar system, named Proxima Centauri, is approximately 4.25 light years away. This means that to reach even the closest neighboring star outside of our solar system in a reasonable time, we must travel at speeds comparable to the cosmic speed limit, the speed of light. Traveling at such a speed would bring many unforeseen consequences that the everyday person does not quite experience in our car drive. So to prepare you for your own intergalactic travels that I'm sure you have planned in the near future, let us explore what it would look like if you travel near the speed of light. To understand the physical changes to your surroundings when you travel near the speed of light, let us first explore the basics of special relativity. Discovered by your favorite crazy-haired German physicist Albert Einstein, special relativity sought to unite two seemingly contradictory physical observations at the time: relative motion and the constant nature of the speed of light. In classical mechanics, the speed of an object varies depending on the speed of the observer. Intuitively, the observer traveling along the direction of the object's motion would say that the speed of the object is less than the speed observed by a stationary observer and vice versa. In fact, the difference between the two observed speeds would be the difference in the speeds of the two observers. However, this rule of relative motion does not seem to apply to light, where observation shows that light travels at the same speed no matter the observer. In order to resolve these two contradictions, Einstein's special relativity proposed that space-time is shrunk and stretched for observers traveling at different speeds. This warping effect is extremely insignificant for observers traveling at normal everyday speed, therefore making relative motion in the classical sense practically true for low-speed scenarios. However, once the observer is traveling near the speed of light, this effect becomes as clear as day, warping space-time so that light would travel at a constant speed no matter the observer. And this results in a bunch of interesting phenomena that we don't get to experience in everyday life. The two effects that we will mostly be focusing on this video are time dilation and length contraction. Time dilation. If your spaceship is traveling at speeds near the speed of light, special relativity tells us that you actually experience time slower than people back on Earth. Effectively, you're jumping forward in time whenever you're traveling at a greater speed, creating a one-directional time machine. When you reach your destination, you will have aged less than those who stayed on Earth. In a way, this would lessen the burden of travel as your experience of the long journey across the galaxy is shortened depending on your speed. The faster you travel, the stronger the effects of time dilation, and therefore the shorter the journey. Currently, it's theoretically impossible for us to travel at the speed of light, but if it is possible, it will appear as if you have teleported straight to your destination, despite possibly eons having passed for those observing your journey. Length contraction. As you may have noticed, if time dilation was the only effect of near light speed travel, it wouldn't make much sense. From the perspective of you in the spaceship, it would appear as if everything is traveling large distances in a short time, possibly at speeds greater than the speed of light, right? Well, this is where length contraction comes into play. When you're traveling at a great speed, the spatial length in the direction you're traveling in actually shortens. Similar to time dilation, the effect of length contraction gets stronger the faster you travel. And with the two effects working in tandem, we preserve the reality that the speed of light remains constant no matter the observer. Now with an understanding of the two basic effects of special relativity, we're ready to tackle the question of what it will actually look like when you travel near the speed of light. As your spaceship accelerates, the first thing you will probably notice is that the objects in front of you are seemingly moving away from you? How does that make sense? Surely length contraction plus our motion should make it seem like we're closing the distance, right? Well, in reality, yes. But that does not mean it is what you perceive. This is because as you accelerate to speeds closer to the speed of light, your field of view warps and widens. Consider this: when you're standing still or moving at speeds significantly less than the speed of light, you can only receive lights from objects within your field of view. However, once you start moving at speeds comparable to the speed of light, it is possible to catch lights emitted from objects that were once within your field of view but have now moved beyond it, making objects that are in actuality behind you appear as if they are in front of you, effectively widening your field of view. This has the added effect of partially seeing an object's side that faces away from you, almost as if this object has been rotated towards you, which has been coined the Terrell-Penrose rotation. As your spaceship accelerates towards the speed of light, the effect gets stronger and stronger, and your field of view gets squished with more and more objects from the side or slightly behind you, making the object in front of you smaller and appears to be moving away from you. However, because the objects are not actually physically moving away from you, the squishing of the object in your field of view will only make the light coming off of them appear so much more intense. So it would be advised for you to wear a nice pair of sunglasses. Nonetheless, blinding yourself would probably be much worse if it wasn't for the effects of blue shifting of light. Blue shifting in this case refers to the incoming light's wavelength being shortened due to the effect of length contraction, making the overall light shift towards the blue end of the visible light spectrum. Therefore, the incoming light will appear to be bluer as your spaceship initially accelerates. But as you accelerate more, originally visible light will shift into the ultraviolet spectrum, making it invisible to the human eye. For the generally brighter blue stars, which already mostly peaks at ultraviolet wavelength, it would mean that the overall visible luminosity from these stars decrease as we travel faster and faster. But this presents an even more deadly problem as these lights shifts into the ultraviolet, X-ray, or even gamma ray wavelengths, making these lights pack quite a significant amount of energy that is deadly to any living organisms on board. So let's hope that your spaceship has a good enough shielding system that blocks out these deadly rays, in addition to shielding you from the rogue proton particle that it may smash into during your journey. And so as you travel faster and faster, more and more space will enter your side view, and the objects directly in front of you will be squeezed into a smaller and smaller space, eventually getting so compact that its intense light will be the only thing visible in your view. This probably is not the most scenic view, so in order to better things up a bit, let the spaceship filter out all the lights and distortion from stars, galaxies, dust clouds, or just any current objects in the universe. Because, well, it obviously has that function. Future tech, duh. And voila, all we would be left with is blank space. Yeah, not very scenic either. Until we reach the speed about 99.9999% the speed of light. By then, you will be able to make out a faint light coming in front of the spaceship. As the ship travels faster and faster and the light becomes brighter, you realize that this is the light coming from the cosmic background radiation, or CMB, aka the oldest light source produced by our universe. Formed about 380,000 years after the Big Bang, the CMB light has been redshifted into the microwave light spectrum due to the expansion of the universe. However, as your spaceship travels at this extreme speed, the incoming light is now blue shifted so much that the CMB light is now visible to your naked eye. This primordial light of the universe has long been the boundary of our observable universe and is now readily available for your eyes to take in. And that is the beauty of our universe. As you journey across the galaxy or even beyond to your destination, the world will always present to you the most unexpected of treasures. So pack your phone, travel pillow, and guidebook for alien civilizations billions of years into the future, and go out there and enjoy your trip. Don't miss out on the scenery!